the second speaker who is here with us, Stewart Grice, who has more than 30 years of experience in the world of jewelry, in particular in the production of alloys, implementation of processes, technical assistance, and production control. He's a vice president of Hoover & Strong, Richmond, Virginia, a member of the Institute of Materials, Minerals and Mining, and engineer of the Engineering Council of Great Britain and Northern Ireland. And he will tell about solders, and we have a presentation which will explore the criteria in order to evaluate the good application of solders and determine whether it is possible to identify guidelines to see what solders will work better in specific situations.
Absolutely no idea what you just said. Thank you. Okay, so I'm going to talk about solders today, and this isn't a heavy technical presentation. It's more of a hands-on sort of investigate it in the factory type of presentation. So what makes a good solder? Can you all hear that okay? Am I good? Yep. What makes a good solder? Is it how it flows, or is it how it wets? Is it its strength, or its melt gap, its hardness, its ductility, or is it a combination of all these properties? After many years of working in technical support within the jewellery industry, I've experienced many examples of one jeweller saying a certain solder is the best solder they've ever used, it's brilliant, it's great, and another jeweller saying the exact same solder is complete rubbish and it's no good, they can't use it. So why is that? So what we want to try and do is to quantify in simple terms some physical and mechanical properties for solders and joining, so we can predict how the joining process is going to perform. And are some solders better suited for joining applications than others? So see if I can get this right. Yes, there we go. So it's the most common form of joining in our industry. Any bench jeweller, any volume manufacturer has to manufacture the soldering process to make their product. Companies that supply solders, they supply them in various forms, and they all have their own unique formulas, usually to suit, colour match their own mill products, sheet wire, etc., castings. And their aim is to give you, the jeweller, problem-free joining without damaging the parent metal or any previous soldered joints. So this study started when a problem occurred that wasn't there before at the company I worked for in Richmond, Virginia, USA, Hoover & Strong. And it was during solitaire manufacturing. And initially, defects were noticed when we soldered 14-karat white heads to 14-karat white shanks and 14-karat yellow shanks, and they both used the same solder for the assembly. So if anyone is unfamiliar, I'll quickly go through the manufacturing process for a solitaire. So the head components are stamped from sheet, they're assembled together, and then they're soldered. And then the shank is made, usually from wire, and it's die struck, and then this is soldered to the head. And then the inside of the solitaire is sanded to get ready for final finishing. And after inside sanding, our finishing department, they noticed that there was an increase in the incidence of porosity in the soldered area, and this was getting worse and worse. And it meant that more repairs were needed to make acceptable product, and therefore it was more cost and more time. Scrap rates eventually became unacceptable, so some investigation was needed. Here we have a few examples of rubbish heads. So when we examined the process, it wasn't only the joining of the head to the shank that resulted in porosity, it was also when we made the heads themselves. We had porosity, we had voids, as we can see here in these couple of examples. Initially, the solder was blamed, and the investigations all focused into the area of the solder to try and identify this problem and then to try and eliminate it. And after starting this study, the type of defect started to occur in several other head shank combinations using different solders. So it became obvious this investigation needed to go deeper. It also became apparent very quickly that the scope of the investigation was going to be huge. We stock 50, maybe 60 different types of solder, and so to examine and characterize all of our solders was going to be a very large task indeed, so we needed to focus a little bit more. So really, what this study about is, it's not a study on solder compositions. These are all very well documented. People that make solders know them. It's not a study on solder development and how to make the ultimate solder. It's a grassroots analysis on what does and does not work. So we decided to investigate several solders around a common carriage, but with different compositions, flow temperatures, and melting ranges. We'll document some simple experiments to investigate wetting, flow, joint geometry, and we hope to determine what variables have the greatest effect on a successful soldering operation. And hopefully from this we can form a guideline to look for what is apparent when selecting a solder and a process. And I'm going to skip that slide. So there are several basic principles that apply in jewelry applications to achieve successful solder joints. And one of the most important aspects is joint preparation. All parts must be a tight fit at the interface. And there are many joint configurations to choose from. We have butt joints, lap joints, T-joints, strap joints, many different types. The choice is going to depend on what you're making and what makes it aesthetically pleasing. Joint faces always need to be clean for wetting to occur. So filing and sanding is recommended to clean away dirt and grease. And the surface roughness is also beneficial because it can help by reducing the contact angle of the liquid solder, so it enhances the capillary action. And there are several basic methods of soldering. So at the bottom, sort of base level, you can use a gas torch, which is what a bench jeweler will typically use. You can use an atmosphere-controlled batch furnace for batch production. You can use an atmosphere-controlled belt furnace for continuous volume production. And you can use induction heat sources. These are typically used in things like chain manufacturing or high-temperature solder applications. So when torch soldering the joint, the area must be heated and not the solder. Everybody knows this who's a jeweler, but it's worth reiterating. Solders always flow to the area of greatest heat and not away from it, so that's how you do it. Time at temperature should be kept to a minimum to prevent excess flow and excessive diffusion of any excessive diffusion into the parent metal or any volatilization of low melting point constituents from the solder, which can lead to porous joints. Both torch and furnace methods can use solder paste, but we're not going to go into these for this study. They're an entirely different study that could be looked at some point. So, the World Gold Council outlines the basic requirements for a solder alloy. So first of all, it's got to be of the correct carriage, or as we call plumb in the US. It's got to be a good color match to the parent metal. It's got to have suitable mechanical and physical properties, so strength, ductility, wear, tarnish resistance. It's got to have a liquidus lower than the solidus of the parent metal, or metals. It's got to have a suitable melt range or melt gap. But most importantly, it's got to be able to be primary manufactured into sheet or wire by a solder manufacturer. There should be no problems with melting or casting, rolling, or scrap recycling. A solder can be great for joining, but if a supplier can't make it into a saleable product, then it's not a good solder. Next slide. Here we go. So it's generally accepted that solders should have a sharp melt gap for the best results. For gold solders, this often means they are based around the eutectic valley in the gold-silver-copper system, and this not only keeps the melting temperature low, it also keeps the melt gap narrow. Some solders do have quite broad gaps, but this is usually a design around color considerations and where they sit in the soldering process. Color match can also be difficult the further away a solder is from the parent metal in melting range. As a general rule, easy and extra easy solders tend to be inferior to medium and hard solders as far as colour match goes, particularly when you're talking about yellow gold solders. The elemental additions you have to put in there to depress the melting point, such as zinc or indium, tin, gallium, and in the US, cadmium. These are all commonly used. These tend to affect the colour, particularly when you're looking at yellow solders, and they bleach them. And it's well documented. I know in Europe you typically don't use cadmium solders, but they do in the US still. And cadmium does improve flow and improve wetting, but it's very toxic. So I'm not going to go into that, but I'm sure everybody understands the dangers of cadmium, sorry. So to start the project, we did a survey of solders and their published temperature data from 3 solder suppliers, one of them being the company who I work for. And this is what we found. So none of this data that a jeweler or a manufacturer gets is composition-based. It's just published data on melt gap, melt range, and whether or not it contains cadmium. Regardless of what else there is in there, all but one example of the cadmium solders cadmium-free solders rather, has a narrower melt gap than the cadmium-containing solders, which should be very beneficial when used in action. So let's have a look at some of the experiments we looked at. So, as I said before, we wanted to look at the effect of solder composition on joining performance for all carats and colours, but this is way out of timescale, way out of budget. So we concentrated on 14-carat solders. The bulk of jewellery in the US, and indeed, I believe, in quite a lot of Europe as well, is made from 14-carat, so that's what we decided to look at. And jewellers don't know the composition, nor manufacturers if they don't make their own solders. They don't know the composition of the solder they buy, nor do they have access to that information. Manufacturers tend to guard their formulas, and they don't give this information away. They only give the information on whether cadmium is going to be in there or not. So with this in mind, we decided some simple tests to compare solders based on the information available to the jeweller. So the colour, the grade, what the melt temperature is, what the flow temperature is, and whether or not it contains cadmium. This is the only data that's typically available to the purchaser. So we chose a relatively simple study. So we did 2 14 yellow cadmium-containing solders, we did 2 14 yellow cadmium-free solders, and we did 2 white cadmium-free solders. And again, as you can see from these melt gaps, the cadmium-free versions do have narrower melting gaps than an equivalent cadmium-containing solders. So the type of test we're going to look at, we came up with. On the small scale, a bench jeweller usually works on individual items, one at a time, using a handheld torch, so an open flame, as the heat source. A volume manufacturer is going to assemble multiple items at the same time using jigs, usually in an atmosphere-controlled belt furnace. And you can see a little example of those on the picture there. So for this study, each test is going to be processed in these 2 ways. For torch soldering, boric acid was used as a flux to protect the workpiece, and in belt furnace, cracked ammonia was used as the protective atmosphere. And we hoped this approach would highlight any differences in solder performance between the 2 methods. So the first test we performed was a wetting test. So we took 6 pieces of each solder and we placed them simply onto a piece of carat gold sheet, and then they were melted using the 2 methods outlined above. This would give us an indication of how well the solders wet the parent metal under each condition. And as we can see from the results table, all there on the second top column entitled torch, the torch soldering tests all showed full liquation, the solders wetted okay, there was no balling, there was no evidence of residual solder left. There did not appear again to be any noticeable difference between cadmium and cadmium-free solders. Solder B in the furnace test was by far the worst result, and there seems to have been some liquation of the pieces, but no discernible solder flow and no wetting on the sheet. I think at that point looks horrible. Solders E and F, that are the white gold solders, we showed signs of some wetting in the furnace tests, but again, we could see some of the residual solder pieces in there. So the furnace results may be exhibiting a phenomenon where diffusion of the lower melting point constituents in the parent metal raises the flow temperature of the solder remaining in the piece to a melt point above the temperature set furnace, the set temperature of the furnace. So the remaining solder doesn't melt. Also note that the worst result was solder B, and it came with the solder with the largest melt gap. So from these results, we can possibly say that the solder's chosen are more sensitive to furnace conditions than direct torch. So after that, we decided to do some tensile tests. Excuse me. So a quantitative measure of the strength of a solder and the solder joint can be determined by butt joining two pieces of ground wire together and then performing a simple tensile test. The important factor here isn't so much the numbers, but whether the sample fails at the solder joint or whether it fails in the wire. If it fails in the wire, the solder joint is at least as strong as the parent metal. If it fails in the solder joint, it doesn't necessarily mean the solder is not suitable for manufacturing, providing the breaking stress is high enough. Failure at the joint will either be because the parent metal solder bond is weak, or the solder itself is brittle and it has low elongation. So we took 1 millimeter diameter wire, we soldered them together using the torch method only for this test. It was a little bit difficult to do it in the furnace. And the results here show that only one sample failed at the solder joint, and it was again solder B. And looking at the marker section there on the left, we can see that the failure was through the solder and not at the interface, suggesting the mechanical properties of the solder were the problem here. The tensile strength that was recorded at 363 megapascals, or newtons per millimeter squared, is adequate for most jewelry applications, so there's not necessarily any need to worry about this. It's just not as good as the others in the test. And the results would suggest that mechanical properties of the solder have been compromised due to design considerations to achieve the desired melt range and the desired color. So the third test we did was to simulate a ring sizing operation, and this is one of the most common jewelry repairs there is. So sizing is done by either removing a section of a ring shank and soldering the ends together, or inserting a piece of sizing wire into the shank and then soldering this. Either way, it's a typical example of a butt joint. So to do this, we took some test rings that we made from 3 by 1.5 millimeter round wire, and for each soldering test, we prepared 3 samples. The first sample we prepared with the joint faces butted close together and flush, and we used 1 piece of solder. The next, we actually used feeler gauges to gap it, and we gapped 1/4 millimeter, and then we used 2 pieces of solder. And the third test, we gapped it at 0.5 millimeter, and we used 4 pieces of solder. And for each solder to be tested using the hand torch, the jeweler was instructed to heat the sample until the pieces had melted, and then to remove the heat source straight away. For the furnace tests, the solder pieces were tack welded onto the rings to keep them in position. They were then placed on jigs and put through the furnace, and the furnace temperature was set to about 30 degrees C above the liquidus of the solder. And we evaluated the samples in the following way. We called the solder joint excellent if it was filled and we didn't need to do any repairs to the ring for it to be finished to an acceptable standard, and we scored it 4 points. We called it good if the solder joint had filled, but it needed minor repair, and so we gave it 3 points. We called it average if the joint was filled, but it needed major repair, and we scored it 2 points. And we called it poor if the joint had not filled enough and extensive work was needed, and we only scored it 1 point. And so here are some results for the torch soldered rings. So all rings with the flush joints were excellent, and we can see a little example on the left there. The solder joint was great. We did some microsections and they revealed some minor internal porosity, but it wasn't enough to be considered significant, and they still finished to an acceptable level. The good and the average results for the 1/4 and 1/2 millimetre gap tests were predominantly down to the joint just not filling fully, as we can see on those 2 right-hand pictures there. Some repair work is going to be needed to fill the joint in, but that could have been possible. For the torch soldered samples, the results were acceptable, except for when the gap became too large. All the test results here can be considered scoring relatively high points. And for the furnace tests, only 1 furnace was used, so it was the same belt speed, it was the same hot zone, we just varied the temperature of the furnace. And these are the results we got for the furnace soldered samples. So overall, they were inferior to the torch solder results. This is evident in the overall lower scores. Solder A performed very well, suggesting this solder is well suited to furnace applications, but the other solders did not, with solder B again having the lowest score. And if we can see some of the joints here. As with the wetting tests, like I said, solder B had evidence of the residual solder being present, and it had very poor wetting and very poor flow. All the other tests were acceptable, but needed repair to achieve an acceptable standard. So overall, hand soldering was far more forgiving than furnace soldering, giving consistent results. This doesn't mean that these solders are unsuitable for soldering in a furnace. It just means that significantly more effort needs to be made to set up the furnace. You need to set up temperatures and belt speed and dial it in for your particular application. The results also suggest that furnace soldering is going to be more susceptible to things like varying thermal loads on the furnace. So the 4th test we did was to solder a post on top of a cup setting to make earrings, and this is a textbook example of a T-joint. We used the same test criteria for torch and furnace soldering, and we tack welded the post on top of the earring before applying any solder. And so, unlike the ring sizing tests, all earring tests gave similar results for both torch and furnace soldering, and there was a negligible difference between any cadmium or cadmium-free solders. And again, all except solder B performed well, exhibiting good wetting and good filled joints. And these images can show you, up there on the top left, solder A, either with torch or furnace, sold very, very well. Solder C was the cadmium-free version of that solder. Again, solded very, very well. But solder B was awful in both applications. So why were these tests better overall than the ring sizing tests? There could be several reasons. First of all, the T-joint has a very close gap because the post is tack welded into position in the first place, encouraging a good solder joint. And also, the relatively low thermal mass of the pieces compared to the rings may contribute to this. And it's going to make the test less susceptible to furnace conditions. So the final test we did was to put a core and solder it into a tube. As we can see the pieces here, we designed it to be a loose fit. So we had a tube with an ID of 2.7 millimeters, and a wire diameter is a very loose fitting 2.5 millimeters. And these are the results. I'm not really going to go into these a lot here because the test was not very good. It was a badly designed test. All it really showed us was if the gap's too big, then soldering doesn't work very well. As you can see from the microsection on the right, there's lots of voids in there. And again, we see with the white solder in the middle and solder B, we have that residual piece of solder still evident in there. So that was the end of the testing, but what did the tests show us? What deductions can a jeweler make regarding the performance of the 6 solders chosen, and can we generalize some of our deductions? Well, first of all, it's very obvious that solder B was the worst performer by far. Soldering with the torch generally produced acceptable results, but the furnace tests did not. Had poor wetting, poor flow, and the pieces didn't fully melt. If they actually did, the results was lumpy and they were cratered. So do we consider the composition of this solder unsuitable for joining materials, or is it more to do with physical and mechanical properties? So let's have a quick look. Solder B had the worst tensile results, both for strength and for elongation. As we discussed, this doesn't preclude its use. It just may need to consider not putting it in a high-stress application. So it's probably not going to be great for ear post soldering. It's going to withstand fewer cycles before failure compared to the other solders. Other properties we can look at. Solder B has a very broad melt gap at 83 degrees centigrade. In a furnace environment, it's going to take a significant amount of time, relatively, to raise the temperature of this solder from melt to flow point. So both cadmium and zinc are included in this solder alloy to lower the melt temperature. In this case, the potential is there for either one or both to diffuse into the parent metal or just to volatilize off and change the composition of the solder that you've got left. Either mechanism will result in compositional change over a period of time in the furnace and will result in an increased melt and flow temperature for whatever solder is left. The new melt temperature or flow temperature of the solder might be raised sufficiently so it's above the set point of the furnace, so it's no longer going to melt or perform as intended. And that's probably why we see the residual piece on the furnace soldered test. So we gave this a quick test and we did some analysis on the residual piece of solder that was left in one of the solder B tests. And typically the solder's made up with 10% cadmium. But when we tested the residual piece, it only had 1.33% cadmium in there. So we believe this loss would raise the melting range of the solder above the furnace temperature. It's going to be less significant when using a solder with a narrower melt gap because you're going to achieve liquation very much quicker. And the problem is going to be less significant when the bench jeweler is using it for torch soldering, because in our case in particular, we instructed the jeweler to heat the workpiece until all the solder had melted. So all the solder's going to melt. So what else did it show us? Well, it indicates that if the liquidus of an alloy is lower than the solidus of the alloy to be joined, and the melt gap is sufficiently narrow, and provided the chemical requirements for wetting are fulfilled, any alloy should successfully join any other alloy. So to test this, we took combinations of standard jewelry alloys and put these through the ring sizing tests. So the tests were performed using the jeweler's torch only on this because the melting range of the standard alloys that we were using was actually too high for our solder furnaces. And we got some good results. So we used straight 14 karat yellow gold to join 18 karat yellow gold. So this is just normal 14 karat sheet, 14 karat wire, and we decided to use it as a solder, and it worked very, very successfully. You could arguably say that's one of the best results in the entire test, even better than the solders. So there's a 53-degree difference between the liquidus of 14 yellow and the solidus of the 18 yellow, and the 14 yellow has a 27-degree melt gap. And using flush joint faces, the results were excellent. So the same applied when we soldered the 22 karat yellow gold with 18 karat yellow gold. All the criteria for a solder were met and the results were achieved. A little bit not so good on the 18 palladium white doing the platinum, but those results were also acceptable. So this really showed us that you do not need special solder formulas for things to act as solders. All you need to do is fill the criteria and the operation should work. And the final observation involved joint geometry. So when the joint gap was a good fit, and with the flush ring test samples, we saw that, and the ear stud samples, the solders performed satisfactorily. What seems to be clear from these experiments is that the quality of the joint geometry, when it becomes less than ideal, then the solder performance decreases. And based on these tests, it's fair to say that furnace soldering will exacerbate some of these problems. Although torch soldering does not have the capability for volume production, the jeweler has complete control over the process and can turn up the heat to get the solder fully molten when they need to, and they have the ability to add more solder to the joint when necessary. Furnace soldering is a standardized process and well suited to volume production. And once the furnace parameters and the solder quantities have been determined and dialed in, this method does give consistent results time after time. And the main thing we take away from this is that probably the most important variable in any soldering operation is the joint quality. Even with the best solders, with poor joint geometry, the joint is going to be poor. So to conclude, we began by asking what makes a good solder, and why do some jewelers love a solder and others hate it? So the two predominant jewelry soldering processes were used as baselines, and bearing in mind that any conclusions drawn were limited to the observations made using only the data available to the purchaser. So the color, the solder grade, and the melt range, etc. The following conclusions were decided upon. So cadmium-free solders perform as well as cadmium-containing solders in both torch and furnace soldered tests. Cadmium is known to help with wetting and flow, but the results showed there was no real difference. Furnace soldering appears to be more solder sensitive when you select your solder, and more so than torch soldering. When torch soldering, jewelers have total control of the heating and the soldering operation. The melt gap of the solder is an important property. A broad melt gap can decrease performance, and this is important because this is some of the information that's available to the purchaser. And the melt gap effect appears to be exacerbated when you furnace solder. Low melting point volatiles can be lost, and the change in melting temperature of the residual solder can potentially be raised above that you set on your furnace. And joint quality and geometry is very important. Tight-fitting joint faces give superior results. Large gaps between joint faces lead to inferior results, which require rework, repair, to get them to acceptable standards, and this is time-consuming and costly. So what we take away from this is solders are fillers and they are not joiners. Sorry, solders are not fillers, they are joiners. I got it wrong way around at the end. Yeah. So it's particularly relevant when we're looking at joint geometry or lack of, as the case may be, and provided the chemical and physical properties of a jewelry alloy meet the criteria for wetting, elemental compatibility, and melt gap is sufficiently narrow, it should be possible for any jewelry alloy to be used to join another one. And our final test demonstrated this. So, to define what makes a good solder, it's the ability to wet the parent metal, create a strong metallurgical bond without the formation of deleterious phases, and to have a narrow gap, melt gap, and that is all you really need. And why does one jeweler hate a solder and the other loves it? Quite possibly it's because a lot of soldering is done, and particularly at the bench, it's a very subjective way, and many decisions for or against how it performs are made based on non-technical observations. One possible reason could be that some jewelers don't pay enough attention to their joint quality. So the original problem we had at the company that I work for, Hoover & Strong, so we did a full investigation and we determined that the problem was not with the solder. All the criteria for the solders worked and they all fitted and they were all excellent. When furnace soldered, then something changed. And the problem was with the quality of the joints. So we analysed the production process and we found out that the assembly department had started to pre-finish all the components before they assembled them. It saved them time during their production process, but unfortunately, the effect was to round off all the sharp edges, making the overall fit of the components inferior, as you can see from this last picture here, large gaps. It resulted in the presence of these big voids, and so the solder was acting as a filler, not just a joiner. After soldering through the belt furnace, the components were joined, but not to a satisfactory standard that could be finished without repair work. And the porosity identified was, as you see, voids generated by a function of poor component fit. So we removed the pre-finishing step and the joint quality improved and we were back to normal. So thank you very much.
Grazie Stewart.